In the previous video, we explored how to define and create our own data type using structures in C++ and how to declare variables of that structure or data type. In this video, we'll dive into how these structures are actually stored in memory. The memory layout of a structure depends on the size and alignment requirements of its members. We'll examine how padding bytes are added to ensure proper alignment and how this affects the overall size of the structure. By understanding how structures are stored in memory, you will be able to optimize your code for better performance and memory usage. So let's get started. I will start by defining a structure with data members of different data types. Here I have created a structure with name point and it has three data members. Data member X of data type short, data member Y of data type int, and data member Z of data type double. All these three data members are uninitialized in the definition, and the size of short is 2 bytes, the size of int is 4 bytes, and the size of double is 8 bytes. Now inside main I will create or declare a variable p1 of data type point. So here point is my data type and p1 is the variable of this data type. So this is the declaration where a variable p1 is created of data type point. Now if I place my mouse pointer on the name of the structure, that is point, then a window opens and shows that the size of the structure is 16 bytes and alignment in memory is 8 bytes. Memory alignment refers to the way data is stored in memory, where each data type is placed at a memory address that is multiple of its size or alignment requirement. Memory alignment is set by compiler automatically according to the hardware architecture to increase performance and faster data access. Now let's find out the memory addresses at which the members of declared variable p1 are stored. In order to display the memory address at which a variable is stored, we need to use the ampersand operator or address of operator. So here we will use the ampersand operator to display the address at which p1 is stored and also will display the addresses of all its member variables. The instruction at line 13 point space p1 declares a variable p1 of data type point and memory is allocated for its storage. When the next instruction at line 14 is executed, then memory address of p1 equal to is displayed at the output, and then ampersand p1 will return the address of p1, that is the starting address of p1 will be displayed after the equal sign, and then endl will move the cursor to the start of the next line. And this memory address is the memory address of the first byte of p1. Similarly, the remaining instructions will display the addresses of its individual members p1.x, p1.y, and p1.z. Now let's see the output. First line of output shows the memory address at which first byte of p1 is stored and is represented in hexadecimal format. The next line shows the memory address at which first byte of p1.x is stored, which is same as the memory address of p1. After that, the next lines show the memory addresses of remaining data members. Now let's see how p1 is stored in memory. Each memory location will store 1 byte C20487F798 hex. At this address, the first byte of p1.x is stored. The second byte of p1.x is stored on next memory address. The next two memory addresses are used as padding bytes for memory alignment because the compiler has used a memory alignment of 8 bytes here. So the next data members should be stored at an address that is a multiple of 8. and before that address all extra bytes are used for padding. So the first byte of that next data member is stored at address 79C and the remaining bytes are stored at the next addresses. The next data member is stored at address 7A0. So all data members have been allocated memory space according to their size in bytes, and extra bytes are only added when starting address to store a data member is not multiple of 8. So this is how memory space is allocated when P1 of data type point is declared, and the total size of P1 is 16 bytes including the extra bytes used for padding. Now let's create a structure point with two data members x and y of same data type int. The compiler here is showing its size as 8 bytes and memory alignment as 4 bytes, which means that a data member is only stored at the starting memory address that is multiple of 4. Otherwise, padding will be added. Now here we have created a variable p1 of point and have shown the addresses of its members by using ampersand operator as explained earlier. The output shows the memory addresses of p1.x and p1.y. Now let's draw the memory addresses and see how data members are stored on respective memory locations. 4 bytes will be allocated for each data member. The member p1.x is stored at address 7f8 to 7fb. The member p1.y is stored at address 7fc to 7ff. No padding is required here because the starting address for both members are multiple of 4. So total 8 bytes are used to store the variable p1. Now let's create a structure student with data members name of data type string, id of data type int, and cgpa of data type double. When a variable s1 of data type student is declared, then 56 bytes of memory is allocated to store the variable with 8 bytes alignment. Now let's add code lines to display the addresses of all members using ampersand operator as discussed earlier. The output shows the memory addresses of all members. Now let's draw memory addresses and the respective locations for storage of data members. The 40 byte space from addresses 798 to 7bf is reserved for storage of data related to s1.name. Now here name is of data type string. For string, that space of 40 bytes is used to hold an 8 byte pointer plus some other parameters that point to memory location at which actual data of string is stored. So here only parameters pointing to string name will be stored and no data of string name is stored here. So this area will remain 40 bytes for all string lengths. Next 4 bytes from 7C0 to 7C3 are used to store data of p1.id. Then 4 bytes are added as padding bytes from 7C4 to 7C7. Starting at 7C8, the next bytes are used to store value of p1.cgpa. So total of 56 bytes are used to store s1 of data type student. Now let's display the size of s1 and all members of s1 using the size of operator. The size of operator is a built-in operator that returns the size of data type or variable that is written inside the parenthesis of size of. Now let's execute the lines one by one and see the output. Starting from line 13, when S1 is declared, then memory of 56 bytes is allocated to store S1. When line 14 is executed, then first size of S1 equal to is displayed at output. The size of S1 operator returns 56, so 56 is displayed after string and L brings the cursor to start of next line. When line 15 is executed, then size of S1 dot name equals to 40 is displayed at output and end L brings the cursor to start of the next line. Similarly, the remaining lines display the size of S1.id and size of S1.cgpa at the output, and end L brings the cursor to the start of the next line. In C++, an empty structure is a structure with no members. When an empty structure is defined and its variable is declared or created, then 1 byte memory space is allocated to store its variable according to the rules of C++. Now here we have created an empty structure, and when the variable is declared and size of operator is used to display the size of the variable, then the output shows the size in 1 byte. But why 1 byte? Because the C++ standard requires different objects to have unique addresses. So even an empty structure occupies 1 byte of memory. This ensures that instances of empty structures have distinct addresses, allowing us to differentiate between them. Thanks for watching this video, and in next video I will explain how structures are initialized and the values are stored in memory.